So we were discussing about the concept of semiconductor and the band concept. Okay. So suppose generally we write or we represent the electronic configuration in this way. That is like 1s to 2s to 2p6 3s2 in this way, right? Now suppose this configuration we write only for one atom. So when you represent this particular configuration in this pattern or in this type of energy diagram, then the lowest level that represents 1s, then next one is 2s, then 2p, then the valence one, it remains at the top, valence band, or valence, not band exactly, valence level in a particular atom, that is the valence shell. So this valence shell is somewhere here. Alright, so this whole figure, that is for one atom. But if you consider two atoms which constitutes a molecule, then for this two atom what we can do is, when you draw the diagram, then it looks like this, because here for two atom we get two 1s level like 1s and 1s star, we get two 2s level like 2s and 2s star, we get two 2p level, okay, in that way. So that is for one molecule, but in a particular solid we have a number of molecules, and for all these molecules now we get a number of 1s level, a number of 2s level, a number of 2p level. So in that case this this is following, or this is making a band, not a single line, but it is forming a band. So if this band, for valence level also we will get the same kind of band. Suppose for 3s also, for a number of molecule we will get many 3s level here, and all this 3s level will form a band, and this band is called valence band. So we can say that the electrons present in valence band can only be removed, because we know that whenever electrons are removed from an atom, it forms, or those electrons are removed from which shell? From the outermost shell. So that means from the valence level or valence shell. So similarly in valence band, whatever electrons are present, those electrons are only able to move, able to not move, able to detached from the particular atom. Okay, and when these electrons are free to move, when they come out of the valence band, then those electrons forms another band, that is the conduction band. So here we got the concept of valence band, where the number of electron present can be removed or can be excited to which band? To conduction band. And the electrons which are present in conduction band, those electrons can only move. Alright, now the concept of energy band diagram for conductors, semiconductors and insulators. See, in case of semiconductor, here you can see that we have drawn a conduction band and valence band, and this is the valence band, this much is the valence band, and this much is the conduction band. So this valence band and conduction band both are overlapped with one another, and since they are overlapping with one another, the number of electrons which are in valence band are also in conduction band. So what is the meaning of it? That means those electrons can easily flow. Okay, the reason is that why these electrons can easily flow, what is the reason behind it? The reason is that, suppose in a metal, suppose for example sodium, if you take sodium is a metal, right? So if you take the concept of sodium, in sodium when we write the electronic configuration, it is like 281. So the outermost electron, how many electrons are there in the outermost shell? That is 1. So this one electron, it has a tendency to come out of the particular atom, isn't it? So that the atom can get its nearest this one what to say, inert gas configuration 28. Alright, so we know that for all the metals, in fact this type of configuration is there. As a result, the electron present in the valence band or in the valence shell are very loosely bound with the nucleus. So in fact in room temperature the electrons can move. Okay, and those electrons are called what? They are called free electrons. So that is why for conductors the conduction band and valence band are overlapped with one another. Now suppose for semiconductor, so semiconductor we know that they are tetravalent. Tetravalent means in the outermost shell how many electrons we have? 4 electrons. Okay, so for semiconductor, and since covalent bond is present in semiconductor, it is the electrons which remain there, those electrons generally remain in which band? In valence band. But yes, in semiconductor the difference in energy between conduction band and valence band is less than 3 electron volt, which can be achieved by applying some temperature or by applying some other form of energy. That means if you apply some other form of energy, the electrons from valence band can easily move to the conduction band, because the energy gap between valence band and conduction band, which is called forbidden gap or band gap, this one Eg, this is less than 3 electron volt. Alright, so if you increase the temperature, then what happened is, okay, now in case of insulators, if we talk about insulator, then the energy gap between valence band and conduction band is more than 3 electron volt, which is very difficult to achieve. If it is more than 3 electron volt, the energy supplied will be very large. It has to be very large to make an insulator or to convert an insulator into a conductor. Alright, in fact, if you remember, we discussed about dielectric breakdown when a dielectric becomes a conductor, right? So for that we need a large or a huge amount of energy. Anyways, in this chapter we are dealing with semiconductor, so our focus is in semiconductor. Alright, so remember that the energy gap or the forbidden gap between valence band and conduction band is less than 3 electron volt in case of semiconductor. Now one more thing that I want to say is, already we discussed about it once in current electricity chapter, that for conductor the resistance and the temperature is directly proportional, right? That means if the temperature increases, the resistance increases. The reason is that when the temperature increases, because most of the electron, I mean almost all the electron which remain for conductors, those electron remain in which band? Conduction band. So when you apply temperature, the electron, the randomness of the electron increases, right? So when the randomness of the electron increases, they start colliding with one another. So once they start colliding with one another, then what happens is their resistance will increase. But yes, in case of semiconductor, what happens when you increase the temperature, then this temperature is helping this electron to move from valence band to conduction band, and once the electron reach to conduction band, its conductivity increases, or in other words resistance decreases. So it is inversely proportional. Okay, then we will proceed to the next topic, this one, types of semiconductor. Okay, one more thing that I have to say is that here, see one thing, suppose when you are applying sufficient amount of temperature, then this electron from valence band, suppose this electron from valence band, it is moving to conduction band. So when one electron moves from valence band to conduction band, here in the valence band we are getting one vacancy. Okay, this, or we can say that here there is a deficiency of electron, and this deficiency of electron is called hole. So what is hole? Hole means it is the positive charge. Positive charge, why do we say positive charge? Because it is the deficiency of negative charge or deficiency of electron. So in the same way, suppose if here I have drawn 5 electrons, 2 this side, 3 this side. So if all these 5 electron moves to conduction band, how many holes will be created in valence band? 5 holes will be created. So these 5 holes will be considered as positive charge carrier, and the electrons which are moving to conduction band will be considered as negative charge carrier. So in semiconductor we have two type of charge carrier. One is positive charge carrier, these are holes. One is negative charge carrier, which are electron. And for this particular semiconductor, the number of electron and the number of hole is same, because if I say that all these 5 electrons are moving to conduction band, then how many holes will be created? 5 holes. So number of electron in the conduction band means 5, and number of holes in the valence band is also 5. So number of electron is equal to number of holes in this type of semiconductor. Okay, another thing, suppose how holes move. If I say that this electron is moving from valence band to conduction band, there is a deficiency of electron. Now this deficiency of electron will be filled up by another neighboring electron. Suppose this electron is coming and filling up this hole. So if this electron is filling up this hole, now that means in this place there will be formation of a hole. Okay, now this hole will be filled up by nearby electron, this electron, then that means here again another hole is created. So in this way, if you see, actually the holes are not moving, but it seems like the holes are moving. Initially we had one hole here, now it is here, then it is here, so that means the hole is moving, but actually hole is not moving, electrons are moving. So that is why these holes are also considered as a charge carrier, because there it seems like the holes are moving. Okay, then we will proceed to the type of semiconductor. Okay, types of semiconductor. First one is intrinsic. Intrinsic means just now whatever I have discussed about semiconductor, those are intrinsic, means only one type of atom will be present. Suppose semiconductor means metalloids like silicon, germanium, etc. So if I consider silicon, or if I take a particular block of silicon, then only silicon atoms will be there. So what type of atom, how many types of atom will be there? Only one type of atom, which is silicon. No impurity is added. So those are called intrinsic semiconductor. Okay, when no impurity is added. But if impurity is added, and in case of intrinsic, the number of holes and the number of electron becomes same. Just now I told you, right? But in case of extrinsic, extrinsic means now impurities will be added. This is called doping. Impurities will be added. Suppose for example, two types of impurity generally we use. As I told you that silicon or germanium, they are tetravalent. Tetravalent means their valency is 4. But what type of impurity do we use? In one case we use pentavalent impurity, in one case we use trivalent impurity. So we will discuss about this one, extrinsic semiconductor, which is of two types, N type and P type. We will discuss about these two types in next video. Thank you.